Hey everyone, gonna go over assessment 10 stuff. I'm gonna try and make a full study guide for you, okay? So go through the majority of chapter 10 without the first few sections on like altering a carbon skeleton. Just use the examples in classes. If you change the carbons, then you change the carbon skeleton. Okay, I'm just gonna go over like pure synthesis steps, things we need to memorize, things we can use in the future. I have a few of them here. So this will be the first video, goes up to I think 10.4. Okay, so 10.3, 10.4 here. 5, 6, 7, 8, maybe the next video, and wrap it up with what's left, probably just epoxide. So maybe 3 videos, 4 tops. Pause the video and try these, okay? If you need to refer to your book, refer to the book on these steps. And then go over and do it again, okay? Try and get these memorized, what these reaction conditions are going to do, okay? First 2 problems here are draw the products. This one, draw on top of the reaction arrow, draw the reactant that's missing. And this one's gonna be just 2 steps, okay? So it's not like a full synthesis problem, but go ahead and draw what would be in the middle, draw what would be at the end. Okay. Pause the video, try on your own. And now I'm going to start with that first one here. The first 2 are 2 ways we can make ethers, okay? The top one is our Williamson reaction for making ethers, involving an alkyl halide and then a methoxy group, some type of oxygen-containing species that can work as a nucleophile, okay? And then our second one is our condensation using either sulfuric acid or phosphoric acid and an alcohol, okay? So we know we're going to make an ether. In the first one, it's just a substitution reaction, okay? So if you were to draw out the full mechanism, which sometimes you do in synthesis problems, sometimes you don't, okay? I'm going to go ahead and get rid of that spectator ion, and it's just an SN2 reaction, okay? And my A product solvent there, strong nucleophile here, boom, SN2. Now, this, and I've made my ether, okay? I've made an asymmetrical ether. Williamson ether synthesis, our Williamson ether synthesis can give us asymmetrical ethers, okay? We could put whatever we wanted on this bromine down here, these carbon changes we could alter, and they would be different down here, and then we can change whatever we want on our oxygen, and we can make something asymmetrical if we wanted. So just a simple substitution reaction there. Our condensation reaction, okay? I can make symmetrical ethers, and I can use H2SO4. I can use sulfuric acid, or I can also use phosphoric acid. Either one will do here, okay? Condensation, I'm going to be left with 2 larger molecules interacting, and I'm left with a smaller molecule. Usually water, okay? Sometimes water will be drawn. I'll go ahead and draw it in this example. It's at the end, we can either use HSO4 minus as a proton acceptor, or we can use sometimes water if it's provided. Okay. Actually, water. We're gonna make our own water. Okay, we're gonna make our own water. So maybe it's not provided. Maybe it's not provided. We're in very acidic conditions here. So the first step in this reaction, our condensation. Rewrite this molecule so it's explicitly drawn here. Very strong acid. It's going to want to dissociate. I have an oxygen here with a lone pair. This is going to be my first step in these acidic conditions. I'm going to protonate my oxygen, and I'm going to be left with water here, which is a good leaving group. Really good leaving group, and then I also have HSO4 minus. All right. Okay, I've made water, really good leaving group. Let's make it leave, okay? Now, I said we're gonna make a symmetrical ether. Okay, in order to do that, we need the same molecule to interact with itself. So one molecule over here, the same molecule over here. Put them together, they're symmetrical, okay? That is this condensation ether synthesis, okay? Made a good leaving group. I have another one of these 2 propyl alcohols, 2 propanol floating around in my solution here that it can interact with. I have a lone pair here, okay? Attack our carbon and make water leave, okay? I'm gonna write this down here. No, I won't. I'll write it like that, and this was on my reaction arrow. Okay, water's gonna leave. I have 3 carbons here. 1, 2, 3. That oxygen is bonded onto that. This oxygen is bonding to these 3 carbons here. 1, 2, 3, 1, 2, 3. My oxygen is bonding on there, right there. And then I have 3 carbons also bonded on the other side of the oxygen when it attacks. Don't forget the H, and I'm bonded with 3 things, so I still have my explicit positive charge there. Okay? Now to get rid of that proton, we made water, okay? Water left. So we can go ahead and write our final step here. HSO4 minus, H2SO4 is a really strong acid, HSO4 minus, therefore, the weak conjugate base. Water probably more likely is going to deprotonate that oxygen, so our final product has a neutral charge. Up there. Those electrons go onto oxygen. My final product is a symmetrical ether, and that's a good sign because I know I'm doing condensation reaction with an alcohol and a strong acid like sulfuric acid or phosphoric acid, so I should expect a symmetrical ether, and that's what I get as my final product. I made, if necessary, HO3 plus and HSO4 minus. Okay, my other products there. Main concern, symmetrical ether, condensation. Those are the steps we got there. Acidic conditions, we protonated our alcohol, made it water, good leaving group, okay? We had another molecule of this interact with itself to get that symmetry. And then our final step, we used the water we made to deprotonate that oxygen. So our final product, our final ether, was truly an ether and a neutral charge and no hydrogen on it. Okay, we've done 2 ways to make ethers. Let's move on now. Okay, another ether type problem, but we're not given the other reactant, we're only given the product. Iodine here, we need to make something that's going to give us this type of ether, okay? So first off, I notice I have an asymmetrical ether. So that should be a good indication that I'm not going to do a condensation reaction, I'm going to do a Williamson synthesis. The presence of an alkyl halide also pretty much gives that away as well. So I need to make a nucleophile here, okay? So something like our ethoxide, for example. Nucleophile here that will give me, it's going to replace that iodine and give me this other tail. Ethers have a carbon chain on the right, or on one side, carbon chain on the other side. If I were to have a nucleophile attack this species here, it would attack at this position we know, and our iodine would leave, okay? So notice in our product, we have something that's attacking this carbon, and then we would put something on this side of the molecule. That's what was this, we can identify this as our starting material here where iodine left, and this here, this species is what attacked it. That's all we need to do. I've identified what was the same, put a little minus charge on there. That was what attacked, okay? So, if I were to approach this problem, again, I would say, okay, I have an alkyl halide, I have an asymmetrical ether, I know I have to do a Williamson type reaction. When iodine leaves, which it will at some point, okay, I'm left with 3 carbons on one side of my ether, these 3 here, let me attack it with this species, they're gonna come together. On top of my reaction arrow, I would just have and I could write Na there, maybe a spectator ion, okay? And when I put these two together, okay, all I have to do is like combine these. Iodine's gonna leave, oxygen's gonna take its place, right? It's gonna attack the same carbon, our leaving group's gonna leave, and we're left with that, okay, with these two combined. All right. Big oxygen there. So if you want to make your own example problems or try some in the book, don't always just do the reaction of the product, because the assessment is likely not going to be like that. It's more likely that you're going to see at least one or two where you have to draw a reactant instead of a product. Okay, so working backwards and like that's good practice as well. Last example for this video, bottom one there. We know that NaH, okay, that hydrogen has a really has a negative charge, a really reactive negative charge. A single proton with 2 electrons, really unstable there. Okay, so it's going to be looking for another hydrogen to bond with and make hydrogen gas. That's what's a lot more stable. NaH, this dissociates, we get H minus. Okay, it wants another hydrogen to bond with. It's going to act as a base and take a hydrogen according to our cardio rules. Our most acidic hydrogen is that bonded to oxygen here. First step here, okay. Our NaH, our NaH deprotonates, and now we've turned an alcohol into a lot better nucleophile. We've given that oxygen an explicit negative charge there. Okay, so that's going to be my intermediate here I have drawn in the middle. NaH is just going to really want a hydrogen, and it's going to deprotonate something so we can use it a little bit more effectively in the future. For example, I'm going to go ahead and redraw this intermediate right here, O minus, and it's reacting with a benzyl chloride. Or chloride in the benzyl position, okay? Okay. Good leaving group. Nucleophile, okay? Williamson synthesis. Alkyl halide, nucleophile, substitution reaction. That's all this is, okay? So, chlorine will leave. Let me draw one of my reactants here. I have oxygen, and now oxygen is making another bond to this carbon here, that carbon there, and then that carbon has a benzene ring on it. Like that. I've made an asymmetrical ether, which is typical of a Williamson reaction. Okay, so here we're going to go through our ethers. Next video is probably going to go over our PBr3 and PCl3. Maybe touch on epoxides a little bit. But yeah, when we go through all of chapter 10 for your assessment on Monday, it'd be like a little study guide for you.